Hey Phys1 kids, Campbell here. In our last video on our circular motion and gravitation unit, we're finally going to talk about gravitation, and in particular Newton's universal law of gravitation. And of course we got to start off with a Kelvin and Hobbes little cartoon because he's awesome. He's trying to get into orbit, but Houston, we have a negative on that orbit trajectory. That's one of the things we're going to look at is critical speed in orbit. What speed does he have to have, and can he get it from a swing? I don't think so. Well, what Newton's universal law of gravitation says is that every particle in the universe attracts every other particle with a force that is proportional to the product of the masses and inversely proportional to the square of their distances, and that's their separation distances. Now, this is gravitational force, or the force of gravity, right? The force of gravity is an attractive force, and its strength is proportional to the product of the masses and inversely proportional to the square of distances. So this is an attractive force between masses. And I think this picture here is supposed to be like the moon, right? You know, the moon orbits the Earth. So if we were to draw a velocity vector, right, its velocity is tangent to the circular path because, you know, circular motion and gravitation go together. And here is the actual equation. So make sure you write that down. The force of gravity, in fact, this gravitational force is equal to this constant g times the product of the masses, so m1, and we call that m1, we call that m2, divided by the square of their distances. Note that this distance is the separation between the centers of the masses. This g is a very tiny number. It's 6.67 times 10 to the negative 11th. The units are Newton meter squared over kilogram squared. And you'll find this value on your equation sheet. Now, this has to be a really small number, because if you think about it, we don't tend to stick to other masses. So if this says that any mass is going to be attracted to any other mass, right? And we know that we're stuck to the Earth, right? The Earth has a huge mass and we're stuck to it. But when we walk down the halls, we don't stick to people that we walk by, right? I mean, their mass is your mass, right? But that force of attraction isn't as big as it is to the Earth, because the masses aren't that big, and this gravitational constant here is very small. So that force of attraction is pretty weak. And the farther the separation gets, the weaker it gets. That's why I say long distance relationships don't work. That force of attraction gets a lot weaker as you get farther away. So let's look at a ridiculous example. You have a 200-gram pickle on your plate. Well, that's a pretty heavy pickle. Next to a 345-gram sandwich. Their centers are 4.5 centimeters apart. And I want to know, what is the force of gravity of the pickle pulling on the sandwich? So what is that force of attraction? Well, we got GMM over R squared. So we got the mass of the pickle and the mass of the sandwich times a very small number. And remember, you need to work in kilograms, right? Mass needs to be in kilograms. And the distance needs to be in meters. So make sure you make those conversions when you do this calculation. And you find that the force of attraction between these, which is the force of gravity, is 2.3 times 10 to the negative 9th. That's why they don't slide together on the plate. Right? There's the frictional force would be a lot higher than that. So, or the Fs max, I should say. So that's why there's no coming together on your plate. You must be thinking, wait, Mrs. Campbell, we already have an equation for the force of gravity, right? We have that mg equation from our last unit on forces. The force of gravity is the mass times the acceleration due to gravity on a planet. But that's the force of gravity on an object that's on that planet. What if we don't know the value of g on a planet? Then what do we do? Right? I mean, I know on Earth it's 9.8, but what about on Mars or Jupiter or Saturn? What's g there? Well, there's a way actually to figure it out. If we put some equations together, all right, we have our Newton's universal law of gravitation, which is g, we'll say mass of planet times mass of object on the planet over the distance between their centers squared. And our other equation for the force of gravity, remember, is the mass of the object on the planet times the acceleration due to gravity on the planet. So if I set these two things equal to each other, because they're the same exact force, right, we get the mass of the object times the acceleration due to gravity on that planet is equal to big G, our gravitational constant, mass of planet times the mass of that object times the distance between them squared. And this is really the distance. If you think about it, you're standing on the surface when we're looking at the force of gravity, or at least the force of gravity at that location, which would be on the surface. Notice that these guys are both going to cancel. So when we rearrange, right, we divide by mx and the mx would go away. So we have this equation. The acceleration due to gravity on any planet is the gravitational constant, that's 6.67 times 10 to the negative 11th, times the mass of the planet divided by the radius of the planet squared. That'll give you the acceleration due to gravity on the surface of the planet. Huh, pretty cool. Now, one question you're going to run into a lot, and in fact, you're going to see it in your packet, you're going to see it, I'm sure, on the unit test for this, is to find the gravitational constant on a planet, that acceleration due to gravity, by comparing that planet to Earth, because we know that G on Earth is 9.8 meters per second squared, right? So if we can compare the Earth, right, so that G would be equal to the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. That's how we get 9.8. So if we could compare a hypothetical planet's mass and radius to Earth, then we could figure out what the acceleration due to gravity on that planet is. So let's take a look at it. We know that this hypothetical planet has a mass, so the mass of this hypothetical planet is equal to 1.66 times the mass of Earth. And the radius of the planet is the same as the radius of Earth. All right, so we have our equation. G would be, the acceleration due to gravity is the gravitational constant times 1.66 times the mass of Earth over the radius of the planet squared. Oops, yeah. Which is the radius of Earth because they're the same. If we factor out this, right, we know that this quantity equals 9.8. So if we factor the numbers out, we get G is equal to 1.66 times G, mass of Earth, over radius of Earth squared. And we know that this is 9.8. So we have 1.66 times 9.8, and that's going to give us the acceleration due to gravity on the surface of that planet, which of course would be 16.3 meters per second squared. Higher mass, higher acceleration due to gravity. Now, let's talk about being in space and this force that keeps objects orbiting other planets, like the Earth around the Sun, or the Moon around the Earth, satellites around the Earth. If we think about the satellite in a circular orbit around the Earth, why does it stay in a circle? Well, there's a force of gravity that is attracting it to the Earth. Without that force of gravity, right, without this force, Newton's first law, an object would maintain constant speed, so it would actually just travel straight. Bye-bye, satellite. But because we have this force of gravity, right, this force of attraction straight towards the center of the Earth, instead, the force is pulling it towards the Earth. Now, if it has enough speed, right, as it falls, it curves around the Earth because it has speed, right? It has velocity as it moves. And so the Earth is curving underneath it. So it continues to travel in a circle, and a circle of constant radius, provided that the speed doesn't change and maybe it doesn't hit some space junk out there in space. So let's take a look at how to find out what the critical speed of a satellite is. So here we have our satellite that's moving with some speed v around the Earth. And so we have our force of gravity equation, that Newton's universal law. So big mass, that's the mass of the planet, times my little mass, the thing that's orbiting the planet, right, divided by their distances squared. Now, the force of gravity is causing circular motion. So the force of gravity is a circular force. And remember that our circular force is equal to mass times that circular acceleration, which is mv squared over r. So the force of gravity then, this gmm over r squared, is equal to that circular force, which is the mass of the object doing the circling, that's the little m, times the speed squared over r, the radius of orbit. And this is always measured from the centers of the objects. So if we look at this and we do some simplification here to solve for speed, you can see that the masses are going to cancel because they're both in the same part of the equation on the same side, or on the same top, on opposite sides. And we're also going to lose an r, right? And if your math is not your thing, right, if we simplify this equation, right, the mass goes down here, so those would be the same and they cancel. The r would go up top, right, it would go up here, and so we'd lose an r. Well, we end up with this equation that the velocity squared is the gravitational constant times the mass of the big planet, the thing that's the big thing, not the orbiting thing, divided by r. So that means that the speed in orbit is the square root of the gravitational constant times the mass. Now this is the mass of the planet, not the thing that's circling, not the thing that's got the speed, over r. This is called the critical speed in orbit. Now, an interesting thing, if you look at the equation, that velocity, the speed, is inversely proportional to the square root of the distance. So that means that if the radius goes up, if I go out farther, I actually have to go slower. What? Crazy, huh? Like a trick question. But the higher the mass of the planet is, the higher speed I have to go, right? A bigger force trying to pull me back in. So interesting relationships in this equation. Now I want you, that's called, sorry, like I said, it's called the critical speed of a satellite or a thing that's in orbit around a planet. Let's take a look at the critical speed of a satellite, a GPS satellite, that's orbiting at a height of 2 × 10⁷ meters above, this is above the surface of the Earth. Now, when we do this problem, all right, we just said that the equation velocity is the square root of the gravitational constant times the mass of the planet that's being orbited divided by the radius, and this is the radius between centers of objects. Centers of objects, right? If you think about what we have here, right? Here's the Earth, and here's my satellite. This distance here is just this. So, not drawn to scale. We need to also add the radius of the Earth to this. So the first thing we want to do is to determine the orbital radius. So I put that in a bad place there. So we need to add that height to the radius of orbit. Now I got to get rid of that too. So we need to add the height above the Earth to the radius of the Earth because it has to be the distance between the object's centers. After that, now we can determine our orbital speed. So the speed is the gravitational constant times the mass of the thing that's being orbited, not the thing that's orbiting, divided by that distance. So our velocity is the square root of 6.67 times 10 to the -11th, the gravitational constant, times the mass of Earth, which is 5.98, times 10 to the 24th, very massive Earth, divided by that orbital radius, 2.638 times 10 to the 7th. If you do that correct, I think you get about 3,900 meters per second. Woo, you gotta go fast. That's why Calvin couldn't get off the swing and get in orbit. Man, he's gotta be going a little bit faster. What would the centripetal acceleration of the satellite be? So then the centripetal acceleration of the satellite, remember that equation is v squared over r. So if I take my 3,900 and I square that and I divide it by the orbital radius, which is that 2.638 times 10 to the 7th. Remember, that's the distance between centers. I'm going to get a value of 0.57 meters per second squared. All right, I'll see you in class.